Valence shell electron pair repulsion theory, or VSEPR for
VSEPR.
short. No, it's VSEPR. It's VSEPR, not VSEPR.
You may have learned about ionic and covalent bonding, but VSEPR describes how the atoms are arranged in 3D space to form molecules. This would be a good time to review your Lewis structures.
First up, we have a simple compound, hydrogen fluoride. There is a single bond between the two atoms, hydrogen and fluorine. As with everything in nature, things are always nice when they come in twos. It is the simplest shape, and they will always form a linear molecule.
Now what if we have two bonds? With two bonds or more, we analyze VSEPR according to the central molecule. In carbon dioxide, we have two oxygen atoms double bonded to a carbon atom, but the two oxygen atoms hate each other. VSEPR theory states that electron pairs will arrange themselves to minimize repulsion.
Why is this? VSEPR theory is based on the principle that electrons will repel each other. Remember, electrons are negatively charged, and negative repel other negatives. You pretend the electron pairs want to get away from each other as far as possible.
In the case of carbon dioxide, the farthest the bonds can be separated is 180 degrees directly across from each other. This results in a linear molecule. Even though carbon dioxide has double bonds, each double bond is considered a single electron region.
If we have 3 bonds on a central atom, for example, boron trichloride, you get something that looks like this. The central atom here is a boron, and it has 3 chlorides bonded to it. The resulting molecule forms a geometry called Trigonal Planar, where the 3 bonds are 120 degrees away from each other in the same plane.
Next off, we have 4 atoms bonded to a central atom. Because this gets more complicated, as all the atoms are no longer in the same plane, we have a physical model to demonstrate what this actually looks like. For our model molecule, we will have methane, which is carbon bonded to 4 hydrogen atoms. In a methane molecule, there are 4 bonding pairs of electrons. Each pair is shared between the central carbon atom and one of the hydrogen atoms. In order to represent the model in the 2-dimensional plane, we use lines and triangles to represent the bonds. We use straight lines to represent the 2 hydrogens in the same plane as the carbon. The filled-in triangle is used to represent the hydrogen going into the page. Lastly, the striped triangle is used to represent the hydrogen coming out of the page. The 4 bonding pairs of electrons will arrange themselves to minimize repulsion. As a result, they will form a shape called tetrahedral, where the angle between each of the hydrogens is 109.5 degrees.
Ammonia, or NH3, has 3 hydrogens bonded to the central nitrogen atom. So you might think, hey, there's 3 atoms, so it must be trigonal planar.
But no, you're wrong. Ammonia actually looks something like this. In order to determine the geometry, you want to focus on the number of electron pairs, whether they be bonding pairs or lone pairs. Consider the valence shell of nitrogen. Every bond it forms with hydrogen, it gives up 1 electron to form a bonding pair. After bonding with 3 hydrogens, there is still 1 pair of electrons all alone, which is called a lone pair. In the case of ammonia, you have removed the bonding electron pair for lone pairs. So although there are 3 bonding pairs, there is an invisible lone pair. The invisible forever alone pair repels the bonding pairs of electrons due to its greater electric repulsive force, forming the structure Trigonal Pyramidal.
Here is water. As you can see, water is composed of an oxygen and 2 hydrogens. The central atom here, oxygen, has 2 lone pairs and 2 bonding pairs. It has the general shape of a tetrahedral, except you remove 2 of the bonding pairs for 2 invisible lone pairs. Pretend you start with a tetrahedral shape, but pluck out 2 of the bonds. The resulting molecular geometry is called bent. The bonds aren't there, but the lone pairs still have an equal amount of electron repulsion. You might think the electrons should be evenly spaced, like tetrahedral, 109.5 degrees. But lone pairs have more repulsive force. This pushes the bonding pairs closer together, forming a smaller angle of 104.5 degrees.
Now we will examine the molecule phosphorus pentachloride, which is one phosphorus atom bonded to 5 chlorine atoms. One of the chlorine atoms is in front of the phosphorus atom. We represent this with a striped triangle for the bond between the two atoms. Another chlorine atom is behind the phosphorus atom. We represent this with a filled triangle for the bond between the two. The last 3 chlorines are in the same plane as the phosphorus. We represent this using straight lines for the bonds. When you have 5 bonding pairs and no lone pairs on the central atom, the molecular shape formed is called Trigonal Bipyramidal.
As shown in 3D, 3 atoms in the central plane are 120 degrees away from each other. Basically, the structure is trigonal planar with extra bonds 90 degrees above and below.
Next up is sulfur tetrafluoride. After drawing the Lewis structure, we see that the central atom, sulfur, has 4 bonding pairs and 1 lone pair. Imagine again the general shape for trigonal pyramidal. You pluck at one of the bonding pairs for an invisible lone pair, and you get the shape called seesaw.
Looking at the valence shell of sulfur, you see that it ends up with a total of 10 electrons. How does this work? Because sulfur is in the 3rd period, it has a d orbital. The d orbital only exists from the 3rd energy level onward, allowing sulfur to have more than 8 valence electrons.
Pluck out another bond pair and you get T-shaped. T-shaped has 3 bonding pairs and 2 lone pairs on the central atom. The 3 fluorines in chlorine trifluoride are in the same plane, so the bonds are represented by straight lines. We also have lone pairs coming out of the page and into the page, represented again by the filled in and striped triangles.
Our final shape is octahedral. In sulfur hexafluoride, we have 6 bonds all at 90 degrees from each other. To show it in 2D, we have 2 bonds up and down in the same plane as sulfur, 2 bonds going into the page, and 2 bonds going out of the page.
To determine the number of lone pairs, first find the number of valence electrons on the central atom. Next, using the molecular structure, find the number of bonding pairs. Elemental beryllium has 2 valence electrons. In the compound beryllium fluoride, there are 2 bonds. Each bond contains 1 valence electron from beryllium, so all the valence electrons of beryllium are used in the bonds. There are no lone pairs. Since there is 2 bonding pairs and no lone pairs, you know the shape is linear.
Sulfur has 6 valence electrons. To form the compound sulfur tetrafluoride, 4 electrons are used in the bonds. The number of valence electrons remains the same, so electrons not used in bonding results in lone pairs. 6 minus 4 results in 2 more electrons not used in bonds, or 1 lone pair. 4 bonding pairs and 1 lone pair means the shape is seesaw. Thank you for watching. You took up like half the height, okay? So the rest of it has to only fill up half.
I think you spelled it wrong, let me check.
VSL. Oh, R.
P.
So P,
B.
Y,
Y.
R,
Pyramidal or pyramidal?
pyramidal. No, it's an I. Here,
Oh,
look.
Oh, you know, it's by print.
And then crumple up.
so bad, Thomas. You crumpled it down.
No, you have the 2 sides.
Gotta get that green going. Gotta get that green.
Are you about that green for hydrogen?
No, I'm doing. I messed it up. Whoopsie daisies! This is messed up.
We need a funny bloopers to end.
Just put in all my bloopers of failure at life. Wait, what is this?
Oh, I spelled this wrong. Oh, I spelled pyramidal. Oh, I spelled this wrong. Oh, you're so retarded, Eddie.